In this video, we'll focus on how bindex is created. And it's not such a simple task.
I am unique.
Every project is unique, and as usual for bindex data generation need to use customization. Bindex is designed for artificial intelligence, and AI must create it.
Pause diagnostics. Command confirmed.
But this process must be optimal, with no security gaps and at an affordable cost. In addition, bindex data must be verified by the developer and provide all the necessary information for its use.
Authorized entry.
Bindex is a kind of boundary. It's data we want to share with others, and you need to choose how to process the input data. You may need to use GenAI's limited capabilities to automatically generate in-code documentation within the project's constraints. This may include writing in-code documentation without an LLM, which would prevent the source code from being shared outside the enterprise. Let's generate and register bindex.json files for the Machai project. I'll be using the Maven plugin's act per module ghostwriter goal with multi-threaded execution and a local bindex repository. Run the bindex act and get result. This will take a long time, even if I use multi-threaded execution. So I'll increase the display speed by 16 times, and while the process is displayed at this speed, I'll explain how it works. Let's look at the current budget status to determine how much it cost us to create the bindex files. $57.68 spent so far. I'm using the built-in bindex act from the main bindex project. This is the starting point for creating bindex. In a modern enterprise ecosystem, we deal with an incredible diversity of project types, build systems, languages, and structural topologies. To navigate this complexity, the bindex pipeline starts with a dedicated project layout discovery boundary. Our goal here is context-aware automation, dynamically discovering what a project is before deciding how to index it. As we see in the diagram, once the bindex action starts, we first check for modularity. Is the module's context populated? If yes, this is a parent project, so we invoke end_task and stop to avoid wasting resources at the root level. If it is a standalone module, we then ask, is this a Maven project? Since this version of bindex supports only Maven projects, detecting a Maven structure transitions us directly to the core mvn/bindex indexing action. If any other build system is detected, the pipeline safely terminates, ending the task with a clear message: project layout is not supported. Once we confirm a valid Maven layout, we transition into episode 1 of the pipeline, building our documentation foundation. Clean, accurate Javadocs are the literal bedrock of our structured context, which is why we trigger a standardized Maven build command targeting protected members and outputting reports directly to a dedicated directory. Once the build runs, the pipeline verifies this output folder. If any errors or warnings occur during generation, bindex doesn't stop. It automatically attempts to fix the underlying documentation issues, allowing up to 3 self-healing iterations. Crucially, this entire process is completely hands-off and zero latency. We enforce a strict, no interactive dialogue rule. The pipeline will never prompt a developer for confirmations or ask follow-up questions. It builds, checks, auto-heals if necessary, and silently proceeds to the next stage once the ground truth Javadoc is ready. With our Javadoc built, we move into episode 2, compiling the actual bindex.json contract. This is where the core transformation happens. We extract project knowledge from 3 distinct sources: Markdown documentation in src/site/markdown, a structured extractor run over our generated HTML Javadocs, and technical dependency data from our Maven effective POM. These raw inputs are mapped directly against our master bindex schema. The pipeline compiles a strictly compliant, valid JSON file. Crucially, we emphasize classification metadata, which powers semantic search, and enforce bulletproof JSON formatting, escaping quotes, and using fully qualified names. We also ensure the manifest includes practical, real-world examples showing exactly how to initialize, configure, and execute the library. Finally, we validate our work. The pipeline immediately reads back the generated file using the get_bindex tool. If validation catches any schema errors, the pipeline automatically fixes them on the fly. Once verified error-free, bindex.json is saved, reported as successful, and ready for deployment. To minimize processing costs, bindex act uses a mini-model for some episodes that doesn't require complex analysis. This includes preparation, Javadoc extraction, and other additional steps. The bindex file generation process in the generate episode eliminates overriding input parameters and utilizes a user-defined model. However, choosing the right model size and capabilities is a critical decision. In the bindex generation process, we prioritize logical synthesis and strict adherence to structural requirements over cost and speed. Investing in a more intelligent model prevents subsequent validation errors and ensures a robust contract for our AI ecosystem. We have reached the third and final episode of the creation flow. Registration. This is where our local, verified bindex.json contract becomes globally discoverable across the enterprise ecosystem. The pipeline automatically calls the register bindex tool, passing the validated manifest we generated in the previous step. Even at this stage, we have a built-in safety net. If the registration service detects any validation or integration errors, the pipeline triggers a self-correction loop to patch the metadata before retrying. Once registered successfully, the system displays the returned, stable bindex ID along with the status message. From this point on, the library is officially indexed, addressable, and ready to be dynamically fetched, understood, and integrated by AI agents and developers alike. This completes the end-to-end bindex compilation pipeline. Finally, our assembly is complete. Let's see what we got. Let's focus first on the sheer volume of work we are coordinating. In our Reactor Summary, we have 8 distinct modules processing. Every single one of these 8 modules built successfully. Now, let's look at the timing footprints. While a clean build and full compile across all modules can take some time, as seen with modules like Ghostwriter at 27 minutes and 35 seconds, GenAI Client at 25 minutes and 42 seconds, and Bindex Core at 22 minutes and 25 seconds, this is because of the heavy lifting of running compilation, deep documentation parsing, HTML extraction, and full registration testing. Smaller orchestration modules, such as our MCP server Maven plugin and project layout discovery, ran extremely fast, clocking in at 5 minutes and 45 seconds and 12 minutes and 15 seconds respectively. Crucially, let's look at the bottom line. The total time for this massive end-to-end Reactor compilation was 1 hour, 4 minutes, and 24 seconds of wall clock time. This demonstrates the power of our pipeline. In just slightly over an hour, we completely compiled, analyzed, extracted context, generated semantic contracts, validated structures, and successfully registered all 8 modules into our active catalog. This is a fully automated, hands-off operation that replaces days of manual documentation engineering with a single, unified build. Let's review changes in the bindex.json files. As you can see, I have 7 updated files. These updates represent the direct output of our newly run generation and self-healing pipelines. Instead of a massive, messy diff of raw code or hundreds of scattered documentation files, our entire pipeline's impact is captured in just these 7 clean, highly concentrated semantic manifests. When we look into the differences, we see that the pipeline has synchronized our latest public API changes, updated our classification tags for improved discovery search, and added more robust, compiled code examples based on our recent codebase changes. Because we only need to track and review these 7 compact files, validating our library boundaries becomes incredibly straightforward. We can verify our entire system's integrations at a glance, ensuring that the contract we expose to developers and AI agents is completely up-to-date, structured, and strictly accurate. Now that our local files are reviewed, let's open up MongoDB Compass to validate our live bindex file registration directly in the catalog database. As you can see, we are looking at our central bindex collection. This is the database that powers our discovery MCP tools, and right now, it displays our successfully registered bindex records. To narrow things down, let's apply a filter specifically for our newly released version, 1.2.2. With the filter active, Compass displays all of our required bindex files successfully indexed under this exact version. Each entry contains the full, validated JSON structure we compiled, now fully addressable and live. By verifying this database state, we confirm that our entire multi-module system is not just built, but officially registered and immediately ready for semantic discovery. Let's look at how we can query these entries. Now, let's take a look at our token spending and model distribution metrics for this entire execution. This chart perfectly illustrates our cost optimization strategy in action. As you can see, the vast majority of our API requests, 92% of the total volume, representing 659 requests, were handled by our lightweight, cost-effective model, GPT-5 Mini. We used this mini-model for the high-frequency, structured processing stages, such as reading files, initial data extraction, formatting, and standard validations. Only 6.7% of our requests, representing 48 highly targeted calls, were routed to our high-reasoning, advanced model, GPT 5.5. These were reserved strictly for the complex generation episodes where deep multi-source synthesis, strict schema formatting, and logical code example generation were absolutely required. Finally, we have a tiny fraction, just 9 requests, allocated to text embedding 005 for compiling our semantic classification tags into searchable vectors. This distribution is the ultimate proof of our balanced architecture. We get the elite logical synthesis of a high-reasoning model where it matters most, while running 92% of our massive, multi-module pipeline on a highly economical mini-model. This keeps our total build costs incredibly low without sacrificing a single drop of contract quality. Now, let's look at the financial bottom line of this entire execution. On the screen, we have our current personal spending dashboard showing our budget limits. To calculate the exact real-world cost of our multi-module run, let's focus strictly on the middle project line item, which shows a current spending of $65.39 for this active billing cycle. To isolate the cost of this specific execution, we need to subtract our pre-build baseline spending of $57.68 from this current total. If we do the math, subtracting $57.68 from our current $65.39, we find that the real total cost for this entire multi-module run was exactly $7.71. Let's let that number sink in. For only $7.71, our pipeline analyzed, compiled, and extracted metadata across 7 distinct codebase modules. Executed 659 cost-effective mini-model calls to handle parsing and structure. Executed 48 highly targeted, high-reasoning model calls to synthesize complex JSON contracts and write fully runnable code examples from scratch. Generated, validated, and successfully registered 7 complete, production-ready bindex.json manifests in our central catalog database. This is the ultimate proof of our cost-optimized architectural design. By combining parallelized execution with a highly disciplined model routing strategy, we delivered a massive, enterprise-grade semantic mapping of our codebase for less than the price of a couple of cups of coffee. With that, we have successfully walked through our entire end-to-end bindex creation, validation, registration, and optimization pipeline. Thank you so much for your time today, and we look forward to seeing how you leverage bindex to unlock automated, cost-efficient, and highly accurate AI integrations in your own projects.